All right, today we're going to tackle something we all take for granted: current electricity. We're diving into this invisible, instantaneous world and uncovering a really cool paradox that, believe it or not, powers your entire life.
I mean, really think about it. You flick a switch and boom, the light comes on. It could be all the way across the room, but it feels like it happens in literally zero time. So, what is actually going on inside that wire to make it so fast? It seems super simple, but the physics behind it? Oh, it's hiding a pretty fascinating puzzle.
So, to get to the bottom of this mystery, we've got to zoom in. I'm talking way in, right down to the microscopic level, to see what this whole flow of electricity is really all about. Okay, get ready for this because it's a bit of a shock. The actual individual electrons carrying the charge inside a regular old copper wire, they are moving incredibly slowly. We're talking about 1 millimeter per second on average. Yeah, you heard that right. That is literally slower than a snail. So, how in the world does the light turn on instantly if the little messengers carrying the message are this slow? Just hold that thought. We're going to circle back to it, I promise. All right, so before we can solve that speed problem, we kind of need to be on the same page about what flow even means in the first place. Like, what is an electric current, really? Well, at its core, electric current is just a steady flow of electric charge. The best way to picture it, think of a river, just flowing smoothly along. It's a continuous, pretty predictable movement. But, as you can probably guess, not all electricity is quite that calm. And that's the key difference right here. On one side, you've got this wild, unsteady flow, like a lightning strike, just this huge, chaotic, unpredictable burst of energy. And on the other side, you've got this steady, controlled flow inside something like a flashlight. It's that second one, that nice, steady, river-like current that powers pretty much everything we use. So that's what we're going to stick with. Okay, so let's go back inside the wire. We're going to zoom right down to the microscopic level again and see how this steady flow actually gets going. So if you look inside a metal wire that's just sitting there, not connected to anything, it is pure chaos. It's basically a sea of these free electrons just zipping around like crazy at super high speeds. But here's the thing. They're all moving in completely random directions, constantly bumping into the metal's atoms. And because it's all so random, if you were to average out all that movement, it adds up to zero. There's no overall flow in any one direction. And no net flow means no current. Simple as that. So that's the big question, right? How do we take this buzzing, chaotic swarm of electrons and get them to stop running around randomly and actually march in the same direction? How do we create a useful current out of that mess? The answer? We apply an electric field. The moment we connect a battery, we create this field inside the wire. And you can think of this field like a conductor for an orchestra. It tops its baton and suddenly gives one single unified command to all those chaotic musicians, imposing order on all that random motion. And this leads us right to this awesome concept called drift velocity. See, even with the field, the individual electrons are still bouncing around like pinballs, but the electric field makes them all collectively, well, drift in one direction. This average coordinated movement is super, super slow. Yep, that's our 1 millimeter per second again. But that tiny collective drift is the electric current. It's literally order emerging from chaos. Okay, so we've got the tiny microscopic picture. Now let's zoom back out and look at the simple, really elegant rule that governs this whole flow on the big picture, macroscopic level. And for that, we have George Simon Ohm to thank. He had this brilliant insight. He realized it's a lot like heat. You know how a difference in temperature makes heat flow from hot to cold? Well, he figured out that a difference in electric potential, what we call voltage, is what causes an electric current to flow. And that gives us Ohm's law, V equals IR. But don't just think of it as a boring formula. It's really a story of cause and effect. First, you have voltage, which is the push. It's the force trying to get the charges to move. Then you have resistance, the obstacle. That's the material fighting back, getting in the way. And finally, you have the current, which is the result. It's the actual flow you get from that push working against that obstacle. It makes perfect sense, right? More push, you get more flow. More obstacles, you get less flow. So simple, but so powerful. So what actually happens when this current of electrons pushes its way through all that resistance? Well, this is where electricity starts to do some really useful work for us.
And it also creates a very, very common byproduct.
Hey, remember all those collisions we talked about inside the wire? Well, every single time an electron bumps into an atom, it passes along a little bit of its energy. And that makes the atoms vibrate more and more intensely. And what do we call a bunch of atoms vibrating like crazy? Heat. This is precisely how your toaster works. The wires in there are designed to have a high resistance, so all those little collisions generate a ton of heat, enough to make your toast nice and crispy.
And we can even calculate how much power is lost as heat. The formula is power equals current squared times resistance. It's often called ohmic loss. And look, this is fantastic if you want heat, like in a toaster or an electric heater. But what if you don't? What if you're just trying to send electricity hundreds of miles from a power plant to your house? Then all that heat is just energy being completely wasted.
And this leads to a really clever engineering solution. Just look at that formula again. The power you lose depends on the squared of the current. That squared part is huge. It means if you can cut the current down, you slash the wasted energy by a massive amount. So what power companies do is they transmit electricity at incredibly high voltages. By doing that, they can deliver the exact same amount of power, but with a really, really low current. This trick minimizes that ohmic loss in the power lines and saves an absolutely enormous amount of energy.
Okay, we've talked about the flow, we've covered the law that governs it, and we've seen how we put it to work. I think it's finally time. Let's go back to the very beginning and solve our little speed paradox.
So let's lay it out one last time. The electrons themselves are crawling along at a snail's pace, 1 millimeter per second. And yet, the light turns on instantly. How is that possible?
And here it is. The answer is that we've been thinking about one speed when there are actually two speeds at play. First, you have the speed of the carrier, the actual electron, which, yes, is ridiculously slow. But then you have the speed of the signal, the get moving command that's sent down the wire. And that signal, the electric field itself, travels at pretty much the speed of light.
So think about it. The second you flip that switch, that electric field, that go signal, shoots through the entire wire almost instantly. That command to start drifting reaches all the electrons at the same time, including the ones that are already sitting inside the light bulb's filament, ready to go. It's not about one electron making a heroic journey all the way from the switch to the bulb. A great way to picture it is a long pipe that's already full of marbles. If you push a new marble in one end, another one pops out the other end instantly, right? The signal, the push, travels way faster than any single marble move. Which leaves us with a pretty cool final thought, doesn't it? When you flip a light switch, you're not really sending a bunch of new electrons racing down a wire. What you're actually doing is turning on an invisible field, a field that instantly organizes the trillions of electrons that are already there, putting them to work right where they are. It's an amazing invisible flow that powers our world.